Okay, thank you. Maybe I take this opportunity to thank all the organizers, Francesco and all the organizers, Mattia, for this really nice workshop. So today I plan to move finally to surfaces, and there's a stepping stone from quivers to surfaces, so I will just say a few words about that most beautiful quiver, in my opinion. This one is already interesting, but this one is really, really well behaved, the Jordan quiver. So if you remember, we introduced the pre-projective algebra for a quiver. The pre-projective algebra for that quiver over C, we work over C, is just C of xy. Okay, just polynomial algebra in two generators. Pre-projective relation just says that this arrow and its dual commute. We've seen this already many times here. And so the moduli stack that we were building the pre-projective, the Coha on, so this T star of rep Q, or if you want to rep pi Q, this is just the stack of zero-dimensional coherent sheaves on A2. Okay, that's it. And so, well, the Coha that we're interested in, this homology of T star rep Q, with a product, this is just, we can say this is the Coha of zero-dimensional sheaves on the surface A2. Okay, so this is a very specific situation when you start to consider stacks of coherent sheaves on surfaces. Usually they are never quasi-compact. They are not global quotients. This one is quasi-compact, and it's a let's say very small piece of the Coha of the full surface. Okay, of all the sheaves on the surface. So let me state the theorem, which whose generalization was the aim of the work I will present today. So this theorem is due to Eric and myself when we consider equivariant parameters generically, generic equivariant parameters, and then there's a refined version due to integral form due to the inevitable Ben. And it says the following. It says that the T, what is T here? T is C star square acting on the X and the Y. So the T equivariant homology of this stack, Coh 0 A2, is isomorphic to the positive half of the so-called Yangian of GL1, affine Yangian of GL1. So this thing is affine Yangian of GL1. So, well, this you have to be a little bit careful. This is almost a definition of this thing through the computation of this Coha, okay? Because you can define the Yangian of an arbitrary Kac-Moody algebra. That you can just take Drinfield's relation and apply it to your Kac-Moody root system, and Chevalier generates and so on. GL1 hat, although it's usually considered the Kac-Moody algebra, it's not really, right? I mean, it's so you cannot just apply Drinfeld relation to this one and hope to get something interesting. So you can almost say this is a definition of the affine Yangian of GL1. But what you can show is that this is a deformation. So this algebra is a deformation of the enveloping algebra of the so-called W1 plus infinity algebra, which is a Lie algebra. So where W1 plus infinity is the algebra of differential operators on A2, on let's say, non-constant differential operators on C2 with the Lie bracket. Okay, so this is an associative algebra, but we consider it with a Lie bracket. And then we take the enveloping algebra. So what is it? It's just spanned by, let me use this notation, dmzn. D is for d over dz, if you want, such that m bigger or equal to 0. I request that n is strictly bigger than 0. And we have the relation dm zn dm prime zn prime is equal to m n prime minus m prime n times dm plus m prime minus 1 zn plus n prime. Okay. All right, so this is the relation. It's pretty nice Lie algebra if you think about it. It's just a very nice, this forms a linear basis, and I just give you the bracket. Okay. And this Coha, this Coha of zero-dimensional sheaves on A2, when you take it with a T equivariant, if you take it in T equivariant homology, then you get a deformation of that one. Okay, and if you don't use a T equivariant homology, then you get exactly that one. So that's a nice result. And let me make some remarks about why this is an interesting result. So applications of that result. So the remark is that, well, first of all, one can define a full Yangian, of which this is just the positive half. Okay, and what is it? It's isomorphic. Well, we have the positive half. Then we have an algebra, which we could think of the Cartan part, which is generated by a bunch of generators, one in every positive degree, and another generator, another collection of generators to be precise, which are the central charges. And then we have the negative part, which is just the opposite algebra of the positive part. So there's an algebra structure on this whole thing. Would satisfy the following. Well, this thing, YH bar of GL1 hat, it acts on the homology, T equivariant homology, of these instanton spaces. So these are higher rank generalization of the Hilbert scheme of points on C2. So for R equals 1, it's exactly the Hilbert scheme of points on C2. Okay, so that's one thing. So you can use that to study the structure of this interesting moduli space. But what was really interesting for exactly understanding and computing certain generating functions of norms of elements in this space was to actually do something a little bit complicated. So you take this affine Yangian of GL1, you specialize a central charge in the correct way, and then you take some completion. So you have to allow infinite sums of positive operator times negative operator, the kind of things you do in say, conformal field theory or vertex algebra. And then there is a quotient on the W algebra of GLR hat. And this one acts on these moduli spaces. Okay, and this action is actually a Verma module. This is a Verma module, a suitable Verma module for not this one, but for this one. Okay, so that's why it's so important to get an action out of this Yangian, to get an action of this W algebra. This is how you can prove the conjecture that physicists had made about the norms and the partition function associated to fundamental classes here. Okay. And maybe let me just make a picture of this algebra, a picture that we can keep in mind for the rest of the talk. So picture is the picture I always like to do. So here, this is the direction of the z variable, and it corresponds to the length. So this coha is graded by the length of the sheaves, right? The stack of coherent sheaves of finite length is a disjoint union over all the length. So this is length of sheaf. And in this direction, we have the homological degree, if you want. And this is the d direction. And the generators are in this quadrant. And so on. And if you look at the action on the instanton spaces, the way this algebra acts, these are exactly the Nakajima operators, which are the action of adding a point, if you want, on the Hilbert scheme. And you can complete the algebra by adding some extra generators. So the algebra is this part. But you can complete by adding the operators of multiplication by tautological classes. Okay, so you have a pretty nice symmetric picture, which, adding this tautological class is exactly adding this Cartan piece. Okay, that's the piece corresponding to tautological classes when you construct the action of this algebra on that representation. And so you have a nice kind of symmetric picture in which you have the tautological classes in one direction and the Nakajima operators in the other direction. And this full, at least the positive half, is generated by these two families of operators. Okay. So the aim of this final lecture will be to explain how we can generalize almost everything to an arbitrary surface, at least under some condition on the surface, some purity condition on the surface. And the almost everything misses out maybe the most, the one thing you would really love to get is this part here. So we have no idea if there exists an analog of the affine W algebra for an arbitrary surface and how one could construct it. But the rest of the picture we can generalize for any surface. So that's what I want to do today. So are there any questions on that A2 thing? Yeah? Yes, so this is the enveloping algebra of the affine W algebra of GLR. So there's you can take the W algebra of GLR, affine W algebra of GLR, at a certain level, whatever, and then there are all these Fourier modes, and then just take the algebra generated by these Fourier modes.
And the representation theory of the vertex algebra for its...
And yes, yeah, I think there are some theorems like that. But yeah, strictly speaking, this is a Verma module for the enveloping algebra of the Lie algebra you can associate to W algebra. Or directly the associative algebra of the vertex algebra.
Just to be clear, in the Yang, do we have one quantum parameter or two?
Two, yeah, H bar is two quantum parameters. But actually, there's one of the two that does not, that is central. I mean, that does not, yeah. Okay, so let me talk about the setup for general surface and tell you about the generalization of this theorem. So let S be a smooth quasi-projective surface. And let us denote by T1 and T2 the Chern roots of S. And let me denote by K0. Yeah, this is just the even compactly supported cohomology. SQ, and let me denote by delta the class of a point. Okay, this is skyscraper sheaf. Okay, so one light motive that you can already put in your head is that T1 and T2, the Chern roots of S, in general, there is no action of the torus, right? And here we saw that the torus was responsible for the deformation, right? If there's no torus, here we really just get the enveloping algebra of a Lie algebra. Here, the deformation parameters that we cannot turn off are the Chern roots of the surface. So when the Chern roots of the surface have some good vanishing property, exactly when S will be symplectic, we will get, again, the simpler non-deformed situation. But OK, that's just jumping ahead a little bit. So for any alpha in this, we can define M alpha as the stack of all coherent sheaves properly supported on S such that the class of F is alpha. So let me give some examples. Let's look at M delta. And so these are derived stacks. So let me just tell you about the classical truncation of M delta. This is isomorphic to S cross BGM because, well, a length 1 sheaf on the surface is just a skyscraper sheaf at a point, structure sheaf of a point, and then there's a group of automorphism. And, well, if I look at, again, the classical stack of a multiple of delta, then I have a support map mapping to the Lth symmetric power of the surface. And the fibers, well, you can imagine that you can stratify this according to the multiplicities of the various points. And the fibers will be the product of fibers corresponding to each point. And the fiber at one point, say, when over n times x, this is this product of commuting stack of GL di. Okay. So it looks like a product of commuting stacks when I look at. So it looks like a bunch of commuting stacks which collide together when points in sim LS collide. Okay, and finally, let me just say that for alpha not of finite length, then M alpha is only locally of finite type. Okay, so for instance, if you take the surface, S is T star of C, then, and you take alpha is, I don't know, R times the class of the curve, then this M alpha is some moduli stack of Higgs bundles of rank R, and maybe the degree is something over C. So these stacks can be quite huge. Okay, and for instance, the entire stack of Higgs bundles, we're not imposing any semi-stability condition here, is one example of these stacks that we're considering. Okay, so nevertheless, these are stacks of objects in some a billion category of global dimension 2. So we can just define the coha there's some work in checking that everything works, especially if it's not of finite type. But let me just say that this can be done, and just so we can define HS. This is going to be the direct sum for all classes of the homology of M alpha. Okay, so always here with Q coefficients. And so in order to define this, M alpha is only locally of finite type. So this is really defined as the limit of homology of open substacks, quasi-compact open substacks. And so this is a topological vector space. Okay, infinite dimensional topological vector space. But it's okay. And inside, we have the space that we're more interested in. It's just the sum over all alpha in n delta of this homology alpha. And these are associative algebras. Okay, these are associative graded algebras. They are graded both by the Grothendieck group, the alpha, and the homological degree. So I should say some names. Okay, so there's a lot of work. Maybe there's work of myself and Francesco and myself. Then before that, there was work in some particular case by Mignetz. And then there's work of Kapranov and Vassereau. And then there's maybe the full version with all the different flavors of derived algebraic geometry you might like is worked out in a paper by Francesco and Mauro. Okay. So maybe a quick remark. I don't want to go into too much subtlety, but when S is not proper, okay, when S is not proper, you might want to consider a compactly supported version of this one. Okay, so what you might want to do is you can, if you want, and it's useful, to replace the homology of M L delta by something which you could call a compactly supported homology of M n delta. And that's defined in the following way. So we have this support map. So we can push down using the star map the dualizing sheaf on ML delta. And then we are on this support map. And whatever we get, we take compactly supported cohomology of that. So we do the Schrick compact support, and then we take H minus of that. Okay, HI here is going to be H minus I. Maybe there's a shift, maybe not. Where pi is just the projection from sim L S to a point. Okay, so this this allows you to get a slightly different algebra. So when you do that, you have some functoriality that allows you to compare a little bit this cohas for different surfaces. So and then you have the following. For any inclusion of one smooth surface into another one, open immersion, we get maps. So from the compactly supported algebra maps into this one, and then restriction map. So this is like that, and oops, like this. These are algebra maps. Okay, so there is some kind of nice functoriality that you can do with these algebras. Okay, and then maybe just to give you one idea of what is in this, what is the first graded component of this algebra. It's very easy to compute from what I wrote above about the m delta. So maybe if I look at compactly supported, maybe of m delta, this is just isomorphic to the cohomology of S bracket U. Okay, and how does that work? Well, if I have a class here, okay, a class X, this just goes to the cap product of X on the fundamental class of M delta. Okay, and to be precise, it's the reduced fundamental class, or the fundamental class of the classical truncation. Doesn't matter. Anyway, so just through Poincaré duality, if you want, you can identify the first graded piece of this algebra with just the cohomology of the surface times bracket U. If you think about the picture for A2, there's no interesting cohomology here. It's just one-dimensional. And what you get is just a one-parameter family of generators. These were the generators on the first vertical line, okay, for A2. If you remember, this was 1, and so I'm talking about these generators. Okay, this is u power 0, u power 1, u square, and so on. Okay, so now I can state the theorem. So it's good that I have a lot of space, because the relations are pretty long, but I still want to write them. Maybe you can stop me if you think it's just too much. So this is a theorem that is due to Melit. I should have written it. I think it's 2L1T. 2L1T. Yeah. Me nets, myself, and Vassereau. So there's one assumption that we would like to get rid of, but for the moment we don't know how to do it. Assume S is cohomologically pure, so that all the cohomology is generated by tautological classes. That's essentially our work works. I mean, our techniques work well with tautological classes. So here's a theorem, maybe one. So the assignment lambda u to the n. This is an element. So if you want, this is an element in the homology of m delta. Maps to Tn lambda. Okay, this is a generator. Gives an isomorphism. Gives an algebra isomorphism from this H0 of S to something that we call the W 1 plus infinity of S. So big W means that it's like the enveloping algebra of the small w, but okay, the S here means that it's going to be deformed, where where this, now I have to give you the presentation for this W1 plus infinity. And this is where I could just say we have quadratic and cubic relations like I did yesterday. But I thought I have to give you at least one family of relations, so that just you can see the kind of monsters you have to study if you want to use this kind of approach. So first of all, Tn, so we have some relations. So one relation is just linearity with respect to the classes. Right, so this is A, Tn of lambda plus B, Tn of mu for A, B in C and lambda mu in the cohomology of the surface. Okay, this is, and now we have, so this type of relations. Tn nu is equal to Tm lambda Tn mu nu. Okay, so this cohomology class here, you can essentially, when you start doing commutator, the only thing that really matters is the product of the cohomology classes. Okay, and then that's the easy one. And then Tm lambda Tn plus 3 mu minus 3 Tm plus 1 lambda Tn plus 2 mu plus 3 Tm plus 2 lambda Tn plus 1 mu minus Tm plus 3 lambda Tn mu. You would like it to stop here and be happy, but no, there's a bit more. So minus Tm of lambda Tn plus 1 S2 mu. So what is S2? S2 is C1 squared minus C2. S2 is T1, T2. Wait, is it really T1, T2? I didn't write it here. Yeah, I think it's T1, T2. Anyway, if not, it's another class of degree 4. Then plus the anti-commutator Tm Tn, and I apply this to C1 delta lambda mu. Okay, and C1 is T1 plus T2. And finally, this is equal to 0. Okay, so here, this is a symmetric, because I multiply by the diagonal, this is symmetric, and so you can put it anywhere. It will be the same thing. Okay, and then there's finally one final relation, which is the cubic Serre relation. Plus the cubic Serre relation, maybe I just write it, the sum for W in S3, W applied to Tm3 lambda 3, Tm2 lambda 2, Tm1 plus 1 lambda 1 equals 0. Okay, so, and this is graded with certain gradings. So when you first look at this, you probably don't like it too much. I warned you last time. But after working with it, you can actually do some things with it. You have to get your hands dirty, but you can actually do something with it. And let me just give you something reassuring. If you're interested in the symplectic case, then all this disappears and becomes a much simpler algebra. So assume C1 equals 0, C2 is minus Q square, so S symplectic. So you can define these algebras for any Frobenius algebra. Right? You replace the cohomology of the surface with the Frobenius algebra, and you can run the same. And then this W1 plus infinity, by the way, it's plus. Did I put a plus somewhere? I should have put a plus here. This is isomorphic to the enveloping algebra of a Lie algebra, and this Lie algebra is just like before, it's just a small deformation. Direct sum for all m greater or equal to 1 and greater or equal to 0, Zm dn lambda. So now I have m n n lambda, but the relations are almost the same. So Zm dn lambda Zm prime dn prime mu is Zm plus m prime. And here I have d plus m prime q n dn prime minus the opposite. Okay. dn d plus mq n prime. You apply it to lambda mu, and you divide everything by q. Okay, so some explicit formula that people who do W algebras, W1 plus infinity algebra will probably recognize. So you can just say that this is the enveloping algebra of a deformed W1 plus infinity algebra. Okay, and the deformation is not so bad.
Olivier, can I ask you a question?
Yes.
So before you were saying that you didn't know how to realize the some WGLI, but you cannot understand how to define some cohomological version on a Goods W algebra for surfaces. Now that you have
So Negutz has some W algebras for certain specific shapes, right? Rectangular.
no, yes,
Or,
some W algebra for surfaces, but quantum because it works at the level of K theory, and they arise by
So-
considering the elliptical algebra and so on.
Yes. So this is this, if you want, is the degeneration of the elliptic hole algebra for a surface, degeneration from K theory to homology. But so if I remember well, he has some huge generating currents. And so, okay, we could try to consider the same huge generating currents here, but to show that this would look like, I mean, to study these algebras is, I think, difficult. But yeah. So we don't understand what construction to do in this case. Yeah.
What is Q?
Q is this number,
C2.
C2. Yeah.
But A2, C.
Sorry? Sorry?
When surface is A2.
It would be 0. But then, yeah, you can still make sense of that. That's a polynomial in Q. Yes, and so what I did not say is that you can, if your surface has a torus action, then you can put the torus in it, and it will arise in these formulas for C1 and C2. So in particular, Q squared does not have to be nilpotent. Okay. All right. So I have 20 more minutes. Okay, so now that we have this theorem, we can describe the size of the algebra. We can understand the algebra, let's say, relatively well. But now we want to be able to use this algebra to do something with it, right? It's nice to have a big generators and relations, but you actually want to have some applications. So what's the idea here? The idea is that Coha of dimension 0, so sorry, H0 of S should act on the homology of interesting moduli stacks or spaces of actual interesting sheaves on the surface, not just zero-dimensional sheaves, right? On infinite length, let me just say that. Sheaves, okay. Let's say of, dimension greater than 0 sheaves on S. Okay, so that's what you want to use this difficult algebraic information to actually get something worth it. So maybe I first define the general formalism. Was coined by Kapranov and Vasro in the name of Hecke pattern. So there are many versions of Hecke patterns, and let me just give you one. So, and let's assume that S is proper, just for simplicity, Okay, just for simplicity. Okay, so a two-sided Hecke pattern is very naive, right? Is a locally closed substack. Let's call it X. Decomposes into a bunch of connected components, X alpha, of the full stack of coherent sheaves on S, and just say MS. And actually, it's better if we just restrict to sheaves which has no zero-dimensional subsheaf. Okay, so this means no zero-dimensional subsheaf. Okay, so either pure one-dimensional sheaves or one- and two-dimensional sheaves, let's say, which satisfies the property that it is just stable under Hecke modifications. Okay, that's very naive. Such that, well, for any short exact sequence like this, with G being of finite length, we have the following. So F should be in X. If F is in X, then epsilon should be in X. Okay, they will be in different X alphas. They will differ by a delta, but so that just means that it is stable under taking a finite co-length subsheaf. Okay, and that might be a right Hecke pattern, and then a left Hecke pattern would be if E is in X and F doesn't have any zero-dimensional subsheaf, then F is in X. Okay, and that might be the right Hecke pattern or left Hecke pattern. So you have many examples. For instance, you just take torsion-free sheaves. You take all dimension 1 sheaves. You can take this Hilbert scheme or Hilbert stack, let's say, of points on S. Okay. So the theorem that's really just free from the formalism says that whenever I have a Hecke pattern, I have an action of the Coha. Okay, and I have the Coha of zero-dimensional sheaves by modification. And I have two actions for a two-sided Hecke pattern. I can see from F, I can go to E, so I can remove a zero-dimensional subsheaf. Or from E, I can go to F, and I can add a zero-dimensional subsheaf. So let X be a two-sided Hecke pattern. Then for any alpha, in this case 0 C of X, I can look at V alpha, which I define as the direct sum for all integers of the homology of M alpha plus N delta. Okay, so all these homology is a left, respectively right, H0 of S module. Okay. So this is just saying that the left module, so you can think of it as a left module for the Coha and for the opposite algebra of the Coha. So ideally, you would like to say that it extends to a left module for the double of the Coha. And so I will state some result like this now. Okay, so for the moment, it's kind of pretty abstract. We have a nice algebra, and we know that it acts, but we don't really have a tool for computing this action. Okay, so let's say it's a bit unsatisfactory. And so what I want to explain now is that, well, we may not have a tool that works for all the homology, but certainly we can do it for the tautological homology. So let me introduce that. And I will not write any more horrible formulas, although I mean, I could. There's one more that I, in principle, should write, but I don't think I will do it. So Junliang introduced tautological classes this morning. I'm just going to consider exactly the same. So let me say that one can define a tautological part, let's just say x alpha, is whatever is generated by these things. You take the integral over s of the cup product of a cohomology class on S with the Chern character of the tautological sheaf. Okay, so this is a coherent sheaf on M alpha cross S, X alpha cross S. Okay, and this is for all values of I and lambda. So this is a subring of the cohomology ring. In certain cases, if X alpha, in certain cases, if I replace X alpha by a nice, say, moduli space of semi-stable sheaves with some good properties, this might be surjective. Okay, but and so there exists a canonical morphism. A canonical morphism from something that we call lambda S. This is just a universal ring, universal supercommutative algebra generated by symbols like that, if you want. Okay, generated by, let's say, symbols, CHI lambda for all I and lambda. This is just a free supercommutative polynomial algebra. And we can just evaluate it on this tautological cohomology of X alpha. Okay, so I think Junliang kind of considered that without saying it. When he was talking about the relations between the tautological classes, he was just considering the kernel of this evaluation map. Okay, so we have this universal ring of tautological classes, and then whenever we fix a moduli stack, we can just evaluate it, okay, through this formula. Okay, and finally, let me denote the tautological homology of X alpha. It's just what I obtain from the tautological cohomology by capping on this fundamental class. And again, maybe we take this reduced virtual fundamental class. Okay, so now the theorem is the following. So let X be a Hecke pattern. Then there's a map from the direct sum of this ring for all n in Z. Okay, so I take many, many copies of this ring, n in Z. Then there's this evaluation map, which is by definition surjective onto the tautological homology. Oops. Let me be more precise. This is the tautological part of V alpha, which is a direct sum for all n in Z of the tautological piece of X alpha plus n delta. Okay. So this is an intertwining operator for the H0 action. So H0 now is W plus 1 plus infinity. where this thing here, let me call it F, is the Fock space representation. Okay, so I did not want to bore you with the definition of the Fock space representation, but one can write some explicit formulas for the action of this W1 plus infinity algebra of S on this big ring of tautological classes. And it's this Fock space is a bit different from the Fock space you might know from Heisenberg algebra. This is not irreducible. This is not highest weight. Okay, but it is some kind of Fock space. And this map is surjective. Okay, so it means that we can understand the tautological piece as soon as we understand the relations in this Fock space. Okay, so it has to be a quotient of this big Fock space by a certain submodule. Okay, so I have 5 more minutes? 7? 9. Okay. So I have 9 more minutes. I'm not going to sketch the proof. I just want to say some ingredient. So I may say that an ingredient is a lot of computations and also some geometric input. So ingredients. So the main technique, main idea, let's say, is we use what's called Negut's lemma, which tells you how length 1 Hecke operators act on tautological classes to determine. So this appears in many of Negut's work in K-theory, but you can do it in homology to determine the action of length 1 Hecke operators. Then we use the fact that our algebra, I did not say it, but is generated by length 1 Hecke operators, okay, and the tautological classes. And then we also specialize. Actually, this is the proof of both theorems. We also specialize to Hilbert scheme of points. To perform some explicit computations, some other explicit computations. Okay, and maybe one remark before I move on to one other application. So one remark is that this extends to action of the double, 1 plus infinity of S, right, the double algebra, which also acts on the Fock space. And this allows us to recover not the full W algebra, but at least the Virasoro part. And this recovers Virasoro algebra. So on any of these two-sided Hecke patterns, we have an action of the Virasoro algebra whose central charge we can describe. Okay, and so I have 6 more minutes. Maybe I just want to give another application that's still work in part in progress, but okay, so let me give another application. This is kind of in progress. So let's assume that S is symplectic. And so it means that this W algebra, say plus 1 plus infinity, is the enveloping algebra of a Lie algebra. And well, this Lie algebra is, of course, just the degree 0 part, the rank 0 part, sorry, the finite length part of the BPS Lie algebra, affinized BPS Lie algebra for the full surface. Okay, so I want to say that G, so there exists a affinized BPS Lie algebra associated to S, such that if you take the full coha of S, not the finite length part, this is the enveloping algebra of this affinized BPS Lie algebra. Maybe I should write like that. This is U of the direct sum for all alpha. And here you have to be a little bit careful because this is a topological vector space, so you have to complete, right, up to some completion. But anyway, we have this Lie algebra that's going to act by adjoint operator on this Lie algebra. Okay, just because everything is a Lie algebra. So a piece of the Lie algebra acts by Hecke operators on the full Lie algebra. And then we have the following theorem. So this is, as I said, in progress with Davison, Enkar, Kinjo, Tasuki Kinjo, myself, and Vassereau. It says the following. So let alpha be a class curve such that alpha squared bigger than 0. Maybe it's possible to drop this hypothesis, but anyway, this is the most important case. So first of all, this affinized BPS Lie algebra of class alpha, this turns out to be just the tautological part of M alpha. So it's just the tautological classes. When you act on the virtual fundamental reduced fundamental class, you get exactly this BPS Lie algebra. So this is kind of a generalization of Markman's theorem for non-coprime case. Okay, so we're happy because we have the tautological classes. And we know how these algebra act on the tautological classes. And then the second part is that there exists an explicit element. It's actually something like T1, no, T0 beta, whatever, such that the adjoint action by this element gives us an isomorphism between this G affinized BPS Lie algebra alpha and the affinized BPS Lie algebra alpha plus delta. And so this is a version of this chi independence. Yep, so I think I will stop here.